I guess we can start. Okay, so welcome everybody for the last session for this semester, and the seminar will restart next semester. And it's a pleasure to introduce Sarai Hernandez-Torres from the Technion to speak about three-dimensional uniform spanning trees.
Well, thank you very much for the invitation. It is a pleasure to be here in the seminar and in Israel with this lovely weather today. And it's also great that the topic of today is uniform spanning trees. And in this talk, we're going to talk about their properties in 3 dimensions. So this is joint work with Omer Angel at UBC and with David Croydon and Daisuke Shiraishi in Kyoto. And the plan for today is first to introduce a model that most of you are already familiar, uniform spanning trees. And I will go as quickly as possible to the main result, that is the scaling limits on the 3-dimensional space. I will also talk about the case when the dimension is 2 to compare to the dimension 3. In dimension 2, we understand the scaling limits better, so it serves you as a comparison of how much we aspire to understand. And of course, our main tool to understand these scaling limits are loop-based random walks. So we are going to talk about that, the connection through Wilson's algorithm, and mostly the properties of loop-based random walks that allow us to study scaling limits. And well, the main part that I really want to talk today are about the metric properties of the intrinsic ball of the uniform spanning tree. So let's start with the definition of the uniform spanning tree. And the most simple scenario, of course, is when we just have a graph that is finite and connected, like the one that I have here on my right. So a spanning tree is a subgraph that passes through all the vertices without creating cycles, like the one I drew here. The collection of spanning trees is finite, so I can just assign uniform measure over it, and a sample from this uniform measure is a uniform spanning tree. Very simple. And our interest today is on set D. So this is an infinite graph, and we do our usual construction in statistical physics. We're going to take growing boxes that eventually fill my whole space. So these are boxes lambda n. For each one of these boxes, I have a measure of the uniform spanning tree. So the weak limit of these measures is the uniform spanning first. So I can be more precise on how we define this. This measure is defined for sets of edges, a finite set of edges like this one that I call B. And I have for each one of these boxes a probability that they belong to the uniform spanning tree. Let's say of this box. In this case, this is one example where they are part of the tree. And as my boxes increase and eventually fill the whole space, the possible connections between the vertices of the edges of the set B are also increase, so it becomes more complicated. And the probability that this specific set of edges B belongs to a uniform sample of spanning trees decreases. So this sequence of probabilities is monotone, decreasing, and has a limit. So we define the limit as the probability that this set of edges B belongs to the uniform spanning forest. So what I obtained in the limit is a measure for subgraphs. In this case, I'm focused on set D. And these subgraphs satisfy that they will pass through every vertex, that they do not contain cycles, but I cannot guarantee that my subgraph is going to be connected in the limit, since the distance between 2 points may increase and eventually be infinite when I get to the limit. And it is a theorem of Pimentel where he proved that first, the measure exists on set D, and it is unique. And well, it is easy to see that it's unique on the way that you choose your sequence of boxes, as long as you eventually fill the whole space and one box is containing to the other. So we actually have a monotone sequence. But it is more important that this uniqueness is in the sense of how you're taking your boundary conditions, as we are taking the limits of these probabilities. So it doesn't matter if we take free boundary conditions, as in my pictures, or wire boundary conditions or something in between, we always get the same limit. So at least for this graph, set D, we have one uniform spanning forest. But even more, Pimentel also proved that the uniform spanning forest is actually connected when the dimension is smaller or equal than 4. So if the dimension is small enough, as it is going to be in the case of today, we can just talk about trees, and for that reason, I will simply call them uniform spanning trees. And in higher dimensions, it is actually the case that the limit is disconnected and you obtain a forest. So this talk today, I'm only going to talk about dimension 2 and 3, and these are the cases that you can keep in mind. And Pearl is going to talk about dimension 4, so it's also going to be a 3. So all trees for today. So this point, well, here in my definition, I define the uniform spanning forest as a measure over subgraphs of set D, but this has a natural, richer structure. And I want to write down my uniform spanning trees in this way. So more complicated because it's going to be a measured, rooted, spatial tree. But this is very simple and is the natural way to do it. So here I have a picture of what could be a sample of my uniform spanning tree on set D. And it has a natural metric, since for any 2 points, let's say X and Y, I know that there exists a unique path between them. So the distance between X and Y is the inherited intrinsic distance of how many edges I have to cross to get from one point to the other. And I also have a natural counting measure. So if I consider a subset of the uniform spanning tree, the counting measure is how many vertices are there in that subset. So essentially what I'm doing is I assign weight 1 to each vertex. And here it's already drawn, but I have natural embedding. Here, when I define the uniform spanning tree as a space, it is an abstract space. But we already know how to draw it because there is a natural embedding of set D onto RD, where we just take the identity over each one of the vertices to the vector with integer entries. So we take the identity over each one of the vertices and interpolate between the edges so that each edge has distance 1. So this gives us embedding that is continuous from our uniform spanning tree as a metric space U onto RD. And to being able to properly define every distance, and as we consider this structure, it is convenient to have a root, so we are going to choose our favorite vertex 0 to be the root. So I obtained this tuple of 5 elements. I have my space with a distance, a measure, embedding, and a root. And all these elements are going to define a measure rooted spatial tree. And this is a spatial tree because if I only look at U with distance, this defines a real tree in the sense that it is a metric space on which I cannot embed homeomorphic copy of the circle to the circle. And it is a spatial since I have this embedding and measure and rooted because I actually have these extra elements. So you can now see the uniform spanning tree as a random element of a measure rooted spatial tree. And of course, we have a space of all the measure rooted spatial trees. So I'm going to call this a space Volti, And these are all the elements, of course. Here I'm not thinking in random terms. This is just a space of metric spaces that has this structure that the metric space is actually a real tree, is locally compact. So of course the tree is not compact. I will only ask that it is locally compact. That has a measure that is locally finite for a measure, a continuous map that embeds that tree into RD and a root. So the set of all these measure-rooted spatial trees is a separable, metricsable space. So here may look, well, a little bit complicated, but each part has a natural metric structure. Because if we have a space of trees, well, even of just metric spaces, we naturally can compare two metric spaces with the Gromov-Hausdorff distance. Well, the locally compact version of it. And since we are rooted, this Gromov-Hausdorff distance also has a rooted version that compares these rooted metric spaces. And if we want to compare the measures for this part, we use the Prokhorov distance. And I'm not sure what happened. I apologize. So, oh, okay, yes. So I had here rooted Gromov-Hausdorff, Prokhorov. And for a continuous map, well, this is just a function onto RD. So we can simply talk about uniform convergence to compare different embeddings. And it is straightforward to define a metric for ball T that is essentially the sum of each one of these elements and gives you a metric for this space T. And this is not something that we propose. It has been already used for the two-dimensional uniform spanning tree when Martin Barlow, David Croydon, and Takashi Kumagai were studying their scaling limits. And it is based on a work on more general spaces of Abraham, Delmash, and Hoscheit, where they proposed metric of distance, but more importantly, they gave a criterion for tightness. So as we are interested in understanding scaling limits of random elements in this space, this criterion for tightness is gold, because we will be able to understand, well, to prove tightness from our understanding of the intrinsic ball. So here is where what we can say about the metric properties of the intrinsic ball is going to be important. So now let's go to what we know about the scaling limits of the uniform spanning trees. And everything is going to be in the context on this space of measure-rooted spatial trees that I have presented. And the idea here is that, well, we want our space between nearest neighbors to be some parameter delta, and delta is going to 0. That's a picture that we have in mind when we talk about scaling limits. So this is, I have on the left, the definition that I have for my uniform spanning tree as one element of this space ball T. And here, my distance between nearest neighbors, I can think that it is 1. But then I can rescale so that the distance is now delta. And you can compare that. For example, if I want to see what is the path between these 2 points, there are not too many options here. So what happened in this tree is that it just went through a straight line. But when the distance, these points are fixed, when the distance between nearest neighbors decreases as delta, then I get more options and the path becomes more complicated. So this is the behavior that we want to understand, what are the macroscopic properties as I'm rescaling my space. So the corresponding picture, well, on the right is easy. I'm just rescaling by delta. But on the left, well, I have to rescale each one of the elements that define my uniform spanning tree in this spaced ball T. So of course the root is 0, so this one is fixed as I am rescaling. This is my root and it's not moving. And whereas my embedding is rescaled by delta. This is essentially how I'm rescaling the picture that I am drawing. For the measure, I'm rescaling by delta to the D, where D is the dimension of the space, because if I fixed ball of radius 1 and I want to count how many vertices are there in that ball, as I'm rescaling, well, this is going to scale as delta to the dimension. So in dimension 3, delta to the 3. And then I have the distance between the intrinsic distance, how this one is scaling. So how I can compare the path between these 2 points as I'm rescaling by delta is going to be a path like this. So this scales as some delta to some exponent beta, where beta a priori is the growth exponent of the path between 2 vertices of the uniform spanning tree. But we know well that this path between 2 vertices of the uniform spanning tree that I draw here on purple is the Lupus random walk. So here beta is the growth exponent of this closely related model and the Lupus random walk. So here is how I'm rescaling my elements of the uniform spanning tree. I get these tuples, scale delta, have an exponent delta to the beta for the intrinsic metric, delta to the dimension for the measure, and delta for the embedding. So this sequence u to the delta as delta goes to 0 are the elements that I want to study that correspond to taking the scaling limits of my model. And this is what we know in 2 dimensions. This is the work of a lot of people starting with the breakthrough of Schramm in 2000 when he defined SLE. And I'm writing this in the language of these measured rooted spatial trees, as Martin Barlow, David Croydon, and Takashi Kumagai managed in their work. So here T denotes the uniform spanning tree in 2 dimensions with its intrinsic metric, the counting measure, and the embedding. And kappa, we know from the work of Technion that it has value 5/4. And this is the growth exponent for the 2-dimensional Lupus random walk. So when I see to these scalings of the uniform spanning tree, the law, it is tight. And as a consequence of work of Nina Holden and Shin-Sun, we know that it also converges as delta goes to 0. And furthermore, we know what the limit object is. In this case, these are SLE curves in the limit from Schramm, and later would work with Greg Loder and Wendelin Werner. So we have a good picture of what happens on the graph set to in the scaling limit. And this is what we proved in the 3-dimensional case. So here I denote by U the uniform spanning tree in 3 and on set 3. So this is the graph where I'm working on with its intrinsic metric, counting measure, and embedding. And here beta, we know that the growth exponent exists, and I will talk a little bit more in a minute. Although we don't have an exact value, but it's some number beta. So now that I take the corresponding scalings of the uniform spanning tree, and I see the law of these measure spatial trees, we know that this law is tight. And if we pick some particular subsequence, it converges over that subsequence. And I would also talk more about why this particular subsequence, or maybe some little variation of dyadic scaling. So we have some restrictions that come from what we already know from the loop race random walk. So this is the main result. And there are two parts essentially, that we have tightness and convergence over a subsequence. And for the tightness, we use this criterion that I told you about, a criterion for tightness that comes from understanding the measures of the intrinsic ball. And for the convergence, what we do is that we have convergence of subtrees. So in our space, we fix some points, let's say K points. We consider the subtrees spanned by those points, and we prove convergence of those subtrees. But convergence including their parametrization of all the paths inside those subtrees. And there are elements of the proof that are common to both tightness and convergence. And as they all use loop race random walks. So we apply Wilson's algorithm rooted at infinity to sample our trees with loop race random walks. We use the existence of the scaling limit of loop race random walks, and that with high probability, the loop race random walk has good path properties. So here, I'm being not very specific about especially this part, what is a good property. So that's why I want to talk about loop race random walks, so I can be more precise on what are the elements that go into these proofs. So in particular, its relation to the uniform spanning tree and what are the properties that I'm interested about it. And you know, loop race random walks, we have a simple random walk on a graph that moves in the usual way because it's drunk. Let's say that it starts in this point and finishes here. So the loop ratio is exactly that. We are going to delete all the loops in chronological order. So my loop race random walk started here and did this loop. So I'm going to erase this first loop, and I'm only going to take the last exit edge. So I'm going to keep this. This backtracking is also going to be erased, although it's maybe you don't want to call it a loop. We don't. We are going to erase it because it's not the last exit edge. And here, although I missed something in the past of my path, is part of my path that has already been erased. So this is where being in chronological order matters, because even if I intersect something that was previously erased, I can use this edge because this doesn't matter anymore. So what I obtain at the end is this path gamma, that is the loop erasure of a simple random walk S. And well, we know this model that was proposed by Greg Lawler in the 80s and has been a huge importance in probability and even more in uniform spanning trees because of this algorithm, Wilson's algorithm rooted at infinity. So here I'm talking about the version where I sample a uniform spanning tree on the infinite space. And in particular, I want to sample the subtree spanned by this set of vertices, x1, x2 to xn. So let's say that I want to see what is the subtree sampled by these vertices that belongs to the uniform spanning tree. And the first step of the algorithm is to do nothing. So what we're going to do is to construct a sequence of trees. And the first tree on my sequence is the empty set. And then I will construct the second one on my sequence of trees. And for doing that, I run a loop race random walk. So I pick the first vertex in my enumeration, and I let gamma 1 to be a loop race random walk starting from that vertex. And it will stop if I hit anything that I have built before. But before I had nothing, so it will never stop. So essentially, this is going to be a loop race random walk that goes to infinity. And this is well defined because well, this is on set 2, but I'm really thinking on set 3. And set 2 is also well defined, but set 3 is easier because the simple random walk is transient. So the number of cycles that I will find at each vertex is going to be finite. So I will only have to erase a finite number of cycles and everything is well defined in the case that I care more about. So this is my first loop race random walk, and I will add each one of the edges so that I construct my 3T1. And I continue in this way. Then I pick my next vertex. I run a loop race random walk from that vertex. In this case, it actually meets something that I have built before. And I stop there and I add that edge to my next tree on the sequence of vertices, on the sequence of trees, T2. And so on and so forth. So when I finish getting all the loop race random walks from x1 up to xn, I obtain a random subtree. And the theorem of Itai Benjamini, Ross Lyons, Yuval Perez, and Oded Schramm is that this 3Tn has the distribution of the corresponding subtree on the uniform spanning tree that is spanned by the set of vertices B. So furthermore, if I were to continue up to infinity, this would be a way to sample all the uniform spanning tree on set D. And this is the reason why we can go from the loop race random walk to the uniform spanning tree, because it is essentially built by drawing loop race random walks. So now, as we want to talk about the scaling limit of the loop race random walk, and for this we need a topology, a space where we are going to define this convergence, and we want to be more sophisticated on the way that we see the loop race random walk. So we have defined the loop race random walk as this loop erasure from the simple random walk. So a priori, what we get is just a sequence of vertices, W0, W1, W2, up to Wn, and this defines a sequence of edges. But we can be a little bit more sophisticated and say, well, this is in fact a path, because you can interpolate between each one of these edges. So gamma defines you a curve from the interval 0t to Rd, just by interpolation. And this has the advantage that we already have a lot of metrics for a space of finite curves. So you can pick your favorite. For example, one that is simple is the Hausdorff metric. Here, it is not specifically for curves, but you can think it as one for curves if you're just looking at the traces. So here I compare the shape of this path with the shape of this other path. And in this case, if I compare the blue path and I call it gamma 1 with the orange path, which I call it gamma, I call the green gamma 2 and the orange gamma 1, then these are close, because if I look in the Hausdorff metric, for every point in gamma 2, I can find one point in gamma 1 that is epsilon close, and vice versa. So in shape, they are close. But this is not a completely satisfactory metric when we are looking for curves, because a curve comes with a parametrization. So in this case, I know that gamma 2 starts here on the top and finishes on the bottom of the screen. But gamma 1 starts at the top and finishes at the top. So if I have a proper metric for my curves, for example, I could say that the distance between gamma 1 and gamma 2 is the difference between their lengths, as here, how large is the interval where they are defined, plus the maximum of gamma 1 SET1 minus gamma 2 SET2, and comparing, how they are traversing the paths for, so here, what this is happening is I'm taking a reparametrization of my paths, I'm traversing them, about the same time, and I comparing what are the corresponding positions. So under this metric, of course, the green path and the orange path are far away, because simply if I look at the endpoints, when s is equal to 1, this endpoint is far away from this other endpoint. So you can see that depending on the metric, some curves may be close, but not as parameterized curves. And if we're looking at the parameterization, then we need to rescale. And for this, it becomes an important element, the growth exponent of the loop race random walk. So I denote by mn the number of steps that the loop race random walk takes to exit a ball of radius n. You know, a loop race random walk starts with a random walk. So let's say that this is S. S is a simple random walk. And the number of steps that it would take is about, well, in expectation, n squared. And when I define the loop race random walk, well, I ignore the loops, so it will get just a simple path. And if these loops are actually macroscopic, even when I'm taking the scaling limit, then this would be reflected on this exponent beta. And this exponent beta, if it is smaller than 2, it means that in the scaling limit, there is an actual difference on the number of steps that I take to advance certain distance between the simple random walk and the loop race random walk. And we say that beta exists if you can give any proper sense to this asymptotic expression. In 2 dimensions, this was done by Technion. So he proved that the growth exponent of the 2-dimensional loop race random walk exists and is equal to kappa equal to 5/4. And by existence, it means that the limit when n goes to infinity of taking, well, the logarithm, so we are comparing exponents of the expected value of the number of steps is equal to 5/4. And in 3 dimensions, this was proved by Daisuke Shiraishi. So he proved that the growth exponent exists on set 3, but we don't have a value, only bounds. So we know that beta is strictly larger than 1, but smaller or equal than 5/3. So here is a pickup, and this is, well, the worst bound. This is closer to the what simulations show that beta should be around 1.6 to 4 ... So this is our approximation to beta on the 3-dimensional case. Well, here I have a simulation of how this would look like. And in particular, beta is smaller than 2. So we have a real difference with the behavior of the simple random walk. So in 2 dimensions, this is what we know about the scaling limit, that it exists, and we also know what the limit is SLE2. First, it was proved for a metric for unparameterized paths. So you took the best parameterization and compare the paths. And if you want to take natural parameterization, this is work of Lawler and Bicklund, where they show this convergence. And well, I think Ariel Yedin is around, and also with Yehuda Yov, they proved that not only for set 2, but you can prove this converges for planar graphs as long as the simple random walk converges to the Brownian motion, which is a natural assumption. So if you already have that the simple random walk in the scaling limit converges to Brownian motion for any planar graph, there is this universality that the scaling limit of the loop race random walk is SLE2. In 3 dimensions, well, it was a breakthrough of Gary Cosma that a scaling limit exists, but it is more restricted in the hypothesis. And we do not have a candidate for the limit. But let me tell you what is the result. And here, I'm just writing down what his paper states. So I have here a polyhedron, and my favorite polyhedron is a cube. And you can consider that the scale is delta for the lattice. So we have this cube, and inside it we have a scaled lattice. And we start a simple, well, a loop-race random walk in a point in the interior of the cube, and we stop it at the boundary of the cube. So we obtain a path gamma that is gamma 2 to the n, where 2 to the n is the scaling of, 2 to the minus n is the scaling of the lattice. So the theorem says that the law of this path converges weakly with respect to the Hausdorff topology, that is the shape of our paths. And well, a very nice reviewer told us that this result can be improved to any subsequence. But it doesn't mean that we can improve the corresponding result for the uniform spanning tree, because we have a limitation for the convergence with respect to the parametrization. So for the parametrization, well, first I want you to compare, this is for the Hausdorff topology, but now I want to consider uniform convergence for the curves. And this one is, as far as I know, only for dyadic scalings, because you need more precise estimates on the probability that a path of your loop-race random walk passes through a particular edge. So here, Shinji and Daisuke Shiraishi state their theorem on a ball. So again, this is a ball with an scaled lattice of distance 2 to the minus n, and you will start as loop-race random walk on the interior of the ball until it reaches the boundary. What you obtain is a path gamma that you rescale according to the growth exponent. So the law of this random path, the theorem is that it converges weakly with respect to the uniform convergence as this lattice 2 to the n goes to, well, the spacing goes to 0, or that is as n goes to infinity. And well, this is a ball, but it can also be proof for a polyhedron as long as the boundary is regular. So these are our the state of the art for the scaling limits of three-dimensional loop-race random walks. And that's what we use to upgrade from a loop-race random walk to the full tree. So this is the scaling limit. We have seen Wilson's algorithm. And now I want to talk about what would be a good path property for the loop-race random walk. And this is an indispensable ingredient to understand well, the arguments, because it is the following. As I am building up, well, my uniform spanning tree on this scale lattice, I want to construct this with loop-race random walks with Wilson's algorithm. But I cannot afford, in terms of probability, to just start running loop-race random walk from every single one of these little vertices. Instead, I want to just run loop-race random walks on a coarser scale. And the heuristic is that, well, this red path should capture most of the behavior of the uniform spanning tree. And what would be that? Because if I start another loop-race random walk from a path nearby, it should hit quickly. But I have to justify why that should be the case. What does it mean for a loop-race random walk to be hittable? And the problem is that in 3 dimensions, this is not always the case. If I have a path, there is a good chance that my random walk from which I build my loop-race random walk misses that path. So I want to justify that indeed these red paths are good enough so that the purple ones are going to hit them fast. And for this, I use this property that we call hitability. And let me tell you what it is about. So gamma is a loop-race random walk on set free. So I start at the origin, and I stop when I leave a ball of radius n, and I obtain a path that will look like this. And now I will pick some vertex x that is epsilon n away from my orange path. So this would be any point x that is that distance. And now I'll let run a simple random walk starting from my point x. So it would be bad. So this is a bad event if even when I start close enough, the random walk still manages to escape, or in other words, to reach distance square root of epsilon n without hitting the orange path. So this is a bad event, and we call it the escape event. So what we want to say is that this doesn't happen with high probability, that most of the paths actually are, well, rough enough so that your random walk is unable to escape up to this distance without touching this Lupus random walk gamma. And this is a very useful estimate of Artem Sapochnikov and Leske Shiraishi. So where they prove that for all n, so this probability is uniform on n, you cannot find an x so that there is a good chance for the random walk to escape. Well, these are various levels of two probabilities here, but what it says is, okay, so for each point, you will have some positive probability that you can escape, or they can be large, they can be small. So the statement says that with high probability, you will not be able to find a point x that has a large probability for avoiding the orange path. So this is very useful because we can say that as we are building up our uniform spanning tree, our paths are hittable. So we are going to we're going to meet them as we construct more and more of the tree. And this is not the only good path property that we use for the Lupus random walk, but it is, in my opinion, the most crucial to understand why these arguments work. So now I can go to the intrinsic ball. So let's talk about its metric properties. And this is a simple proposition that is a good example on how we can handle this and what are the properties that we are interested in. So here I'm comparing the intrinsic ball. So this is the ball with respect to the intrinsic metric. That's why I call it B sub U. So this U denotes that this is the metric that corresponds to the uniform spanning tree with the Euclidean ball. And well, here I am not rescaling the lattice. This is on set3. So what instead of rescaling the lattice, this proposition is rescaling the sizes of the ball by delta. So if I scale the Euclidean ball by delta -1, so this is a large number, and I rescale with the appropriate exponent. So in this case, it's the growth exponent beta, delta to the minus beta, and I leave a little bit of space, lambda -1. Then with high probability, the intrinsic ball is contained in the Euclidean ball. And this is with high probability that depends on lambda. So if I give more space, it's easier for this event to happen. But the important part is that the probability with which this happens is uniform on delta, so it only depends on lambda. And what I want to justify is that this is an upgrade from a property of Lupus random walks to a property of uniform spanning trees. Because for Lupus random walks, we have similar estimates for the growth exponent. So remember that Mn is the number of steps that the Lupus random walk takes to exceed a ball of radius n. And a result of Daisuke, and then, well, together with another result of Shinji and Daisuke, is that Mn is at least lambda minus 1 to n to the beta with high probability. So the number of steps that Lupus random walk needs to reach distance n is of this order. So what it means is that if I consider the corresponding intrinsic ball for the Lupus random walk, so let's call it beta gamma, this ball. That means that if I see lambda minus 1 n to the beta, this is contained on b to the n, the Euclidean ball. If I were just to consider well, a ball for the Lupus random walk. So I want to upgrade this estimate from just one path to many paths. And the idea is as follows, a sketch of the proof. I apologize here. I stated my result scaling the radius, but for the drawings, I will actually rescale the space because it avoids writing down delta minus 1 many times. So for the sketch of the proof, everything lives on a scaled space with distance delta minus delta. Yes, actually it's delta. Delta is a small number, so the spacing is small, delta between the neighbors. So here, the analog of a ball, Euclidean ball of radius delta minus 1. If I'm scaling the space, it would be a Euclidean ball of radius 1. And the bad thing to happen, so something bad, is that I could find an X such that belongs to the complement, some X outside, but somehow it has like a special connection with the origin, like a very fast path between 0 and X. So the intrinsic metric between 0 and X would be a lot much smaller than delta to the minus beta. So this would be something bad, and this is what I want to avoid to happen. But here we can use a geometric insight, and that is, if I want to connect a point outside in the complement of the ball, I necessarily have to pass through the boundary. So I won't aim to control all the points that are on the complement, but I want to control the points on the boundary. So I want to justify that every time that I pass through the boundary, this path is large enough so that I cannot have this sort of red highway. And the way that we achieve that is with an approximation with annuli. So we have annuli that starts here, like this part, and it decreases as k goes to infinity. Well, but it cannot go to infinity because we still live on the lattice. So at some point, the distance between nearest neighbors is actually 1. So we can take decreasing annuli for 1 up to some point k0. And for each annuli, we're going to sample uniform spanning trees using Wilson's algorithm. But with this technique that, well, this idea that I told you before, that we want to do it in a cursor scale so we can have control over the number of Lupus random walks for which we ask good properties. So these are nets that are going to cover the annuli, and these nets have a distance between points epsilon k. So this is decreasing as a power of 2 to the minus k. So to have a picture, and this will be my first annuli, and to distance a half, and each one of these points has distance epsilon 1 between neighbors. And if I put a ball around each one of these points, I would be able to cover all of the annuli. So the idea is to run Wilson's algorithm for each one of the red points, including the origin. And I'm not drawing the paths here, but I'm going to condition that the path gamma infinity, the first one on Wilson's algorithm, is hittable to the point that I'm not going to enter a small region around 0, because I want to obtain the property that for all the paths that I start from these red points, I'm far away from 0. So if I achieve that, well, this is the property that I was talking. I want to avoid this small region of radius lambda -4 around 0. So if I have these properties, then I'm getting that points closer to the boundary are getting the right order of distance to 0. And as I'm taking annuli closer and closer to the boundary, I eventually obtain that the boundary B1, the internal one, is an element of this net at level K0. So for this, all the elements of the net, I have the right distance, in particular for the boundary. And since the boundary disconnects from the complement of the ball, I obtain the estimate that I'm looking for. And for the lower inclusion, you can do a similar idea, but instead of taking annuli from inside the ball, you take annuli from outside the ball and use the corresponding inequality for the loop race random walks. So what you obtain is this inclusion between balls, but we're more interested on what it means about the measures of the balls. So we obtain that the measure of a ball of radius, intrinsic ball of r to the beta, is smaller, well, it's around r cubed, because that's the volume of the Euclidean ball. And under a rescaling, what we obtain is that the volume of an Euclidean, the volume of an intrinsic metric, of an intrinsic ball of radius r, is bounded above and below by r to the 3/beta. And we can upgrade these to uniform estimates for the ball, for the balls of the uniform spanning tree. And from there, we are able to compute the Hausdorff dimension. So this is a final statement about the geometric properties of a subsequential scaling limit. Let's call it U. It has the usual properties. It is complete, locally compact, a real tree. But thanks to these volume estimates, we can say a little bit more about its Hausdorff dimension. And it is, in fact, as we would expect, this exponent 3/beta. So this is the end of my talk. And well, thank you very much for your time here.
Can you show again the last transparency? Last one. Yes, yep. Okay, thank you. Thank you.
Any questions?
Yes, I had a question. Great talk. I was just curious if you had any other models that you maybe, like in 3 dimensions or 2 dimensions, that you conjectured will also converge to a real tree. Like, I don't know, what's an example? Like, yeah, I can't think of it at the moment. Like percolation or something, like or some variant of that. Yeah. Anyway, yeah, that's my question.
Well, percolation is not going to converge a tree because it didn't start a tree. Well, like in 3 dimensions, the thing is that it's not going to be mean field behavior by any. It's I mean, I don't know, but not here. So in 3 dimensions, probably you want to start with something that is already a tree, and what you want to see is that it keeps being a tree, which happens here.
Right.
Yes, that's what I can say about that. In higher dimensions, you can be more lucky and somehow disconnect, but not in 3.
Thanks.
Any other questions? Let's thank Sarai again for a wonderful talk. And we have 3 minutes break. Hey, Perla.
Hi.
How are you doing?
Good. How are you?
Good.
Hi, Sarai. Thanks for the talk. I followed only parts of it because I had to take my kid to school.
And nice to meet you. I was looking forward to meet you in several occasions last summer, but that didn't happen. Last summer.
Yeah, right. You gave the perfect first part